Did you know that the active ingredient in Tylenol, which is called as acetaminophen, is an amide compound? So in this video, we will learn more about amides and how to draw the amide products and how to write their names. First, we'll see what is an amide. So these amides are actually derived from carboxylic acids. So we just have to replace hydroxyl group with an amine group to make an amide. We'll see how this reaction happens. So the reaction that synthesize amides are called amidation or condensation reactions. In this reaction, a carboxylic acid will react with ammonia or primary or secondary amine. So the carboxylic acid will undergo a condensation reaction to eliminate the hydroxyl group from the carboxylic acid and a hydrogen atom from ammonia or the amine that is reacting with the acid. So that's why primary and secondary amines will undergo these amidation reactions, but not tertiary amines because there is no hydrogen atom in tertiary amines. Now we'll see what happens in this reaction. Now in the carboxylic acids, the hydroxyl group will be separated from the carboxylic acid, and that hydroxyl group will combine with one of the hydrogen atoms in the amine or ammonia to eliminate as a water molecule. So the rest of the fragments of carboxylic acid and the amine will just combine to make a new bond called amide bond. So this is called a condensation reaction that requires heat because it needs energy to break up bonds and to form new bonds. So in this example, the propanoic acid reacts with ammonia to form propanamide. In the second example, propanoic acid will react with methylamine. So this is a primary amine to form N-methyl propanamide. So those are just two examples of condensation reaction. Now we'll do a learning check to predict the products of the following amidation reaction. When you have this type of questions, first try to understand what are the fragments of the acid and the amine that will combine to form this product. Now we have this benzoic acid here. So we just need to separate the hydroxyl group from the carboxylic acid. The rest of the fragment from the carboxylic acid will go and combine with the nitrogen atom in the amine. Now, to understand the reaction, I'm going to draw the extended formula for amine showing two hydrogen atoms separately. Now, one of these hydrogen atom will just combine with hydroxyl group to form that water molecule. Now, the other fragment of the amine will just go and combine with the so these two fragments will combine to form the amide. I'm going to draw the amide here. First, the fragment from the carboxylic acid, and this carbon will combine with this nitrogen atom. And then I need to draw the fragment from the amine NHCH3. And the hydroxyl group and hydrogen atom will combine to form a water molecule. So these are the two products from the amidation reaction. We have the answer here. Okay, now we'll see how to name amides. Um, Now, as the first step of naming an amide, whether it's an IUPAC name or common name, first of all, we need to identify the fragments that came from the carboxylic acid and from the amine groups. Now, in this example here, um, the carboxylic acid fragment is shown in this pink color box. And since it has 4 carbon atoms, we know that came from butanoic acid, or we call it as butyric acid according to the common names. Butanoic acid is the IUPAC name. And if you look at the fragment from the amine group, so that should have come from ammonia, because we just need to add another hydrogen atom to predict the initial amine group. So this should be ammonia. Now we have identified what are the carboxylic acid and what is the amine. Now the second step is to convert this um, carboxylic acid name to the corresponding amide. Now, in order to convert, we will just um, drop the oic acid in IUPAC name and replace that with the suffix amide. So the butanoic acid will be changed to butanamide. So you just replace this oic acid by amide. So it becomes butanamide. So that's how the IUPAC name derives. Since this amine is actually the ammonia, so since it came from ammonia, we don't need to do anything for that. There's nothing for us to do with that name. So it will be just butanamide. And here are some other examples. So the carboxylic acid part fragment contains only one carbon, so it should be methanoic acid. Carboxylic acid name is methanoic acid, so the name is changed to methanamide. And the carboxylic acid fragment in this amide is ethanoic acid because there are 2 carbon atoms. So the name would be ethanamide. And the carboxylic acid fragment of this amide is benzoic acid, so the name would be benzamide. Now you can see in all of these instances, the amine is the ammonia, so we don't do anything to the name. The name doesn't involve any naming parts from ammonia. It's just the carboxylic acid. And if you take the look at the common names, the common names would be just butanamide will be named as butyramide because butyric acid, in the butyric acid, you just replace this ic acid with amide to make it butyramide. And formic acid. So this carboxylic acid is named as formic acid according to the common names. So formic acid will convert to formamide. And this is the acetic acid according to the common names. So that will be converted to acetamide. So that's how we give the common names for these simple amides. The common names will be generally given from 1 carbon to 4 carbon atoms containing amides. Now we will see how to name an amide with alkyl groups attached to the nitrogen atom. In this case, we have to incorporate the alkyl groups names into the amide name. So the first step will always be the looking at the carboxylic acid fragment. Since the carboxylic acid fragment in this example comes from the butanoic acid, we will first convert that into the corresponding amide as butanamide. Now, the second step is to look at the amine fragment. In the amine fragment, there are two methyl groups directly connected to the nitrogen atom. Now, in this case, we need to use the prefix N twice to show that there are two methyl groups attached to the same nitrogen atom. So the name would be N, N dash dimethyl butanamide and no spaces in between dimethyl and butanamide. The common name would be N, N dimethyl butyramide. So this is how you will name an amide with alkyl groups connected to the nitrogen atom. Now we will see an example. Give the IUPAC name for the following amide. The first step, as always, is to identify the carboxylic acid fragment. Now this comes from butanoic acid. So we will start with butanamide name. The second step is to identify the amine fragment. Now, in this example, there is a methyl group connected to nitrogen and there's only one alkyl group. So we have to incorporate that fragment name in front of the butanamide. And since there is only one methyl group, we would just name it as N-methyl butanamide, since there is only one methyl group. N-methyl butanamide is the correct IUPAC name for this particular amide. Okay, so that's how we can name amides according to the IUPAC rules. We will see more examples in the problem discussion. Now we'll see the physical properties of amides. Now even though these amides are derived from amines, they have very different physical properties than amines. So unlike amines, most of the amides are solids at room temperature. Only methanamide, which is the amide with one carbon atom, is a liquid at room temperature. So what does this mean? What does it mean by liquid at room temperature and solid at room temperature? So this is all about how their molecular interactions happens at room temperature. Liquid at room temperature means they can easily evaporate, right? So they have a very lower melting point. So that's what it means. And solids at room temperature means their melting points are much higher, or in other words, in order to separate these amide molecules, we need to provide a higher energy. That means these molecules have higher number of intermolecular interactions or much stronger intermolecular interactions. So that's why they are packed tightly to make them solids. Um, Now, if we look at primary, secondary versus tertiary, primary amides have the highest melting points. The reason is they can make or they can form the most number of hydrogen bonds. Primary amides have the highest melting points because amine group can form the most number of hydrogen bonds. Because amine group has these two hydrogen atoms attached and they can make hydrogen bonds with another amide molecule. And the secondary amines are lower because there's only one hydrogen atom, and tertiary amides cannot form hydrogen bonds because there are no hydrogens available to make hydrogen bonds. So in order to make a hydrogen bond, that hydrogen need to attach to either nitrogen or oxygen in this particular molecule. So there are no hydrogen atoms attached in oxygen or nitrogen. So there will be no hydrogen bonding possible in tertiary amides. That means lower intermolecular interactions. So therefore they have the lowest melting points. I have shown here an example of how the melting points are changed when it comes from primary to secondary to tertiary amides, which have the same molar mass. Now, in propanamide, the melting point is much higher than N-methylethanamide and N,N-dimethylmethanamide. The reason for propanamide to have a higher melting point is because that molecule can make higher number of hydrogen bonding because there are two hydrogen atoms available to make hydrogen bonding. Um, because this molecule can make more hydrogen bonding with the same type of molecules, they will have higher number of interactions, and as a result, they will stay as packed molecules to make them solids at room temperature. In the second example, where there's only one hydrogen atom available for making hydrogen bonding. So it has an intermediate melting point, and in the tertiary, there are no hydrogen atoms available for hydrogen bonding. So that means very low amount of interactions, intermolecular interactions, and its melting point is very, very low. So as the available sites for hydrogen bondings are decreased, their melting points are also decreased. So this is a nice example to understand about this intermolecular interactions, how these intermolecular interactions are affecting their melting points. Now, regarding the solubility in water, there is hydrogen bonding variation of amides with water as well. Now, the amides with 1 to 5 carbon atoms are soluble in water because they can hydrogen bond with water molecules. Due to the size of the molecule, it's easier for them to make hydrogen bondings. And also, they they will be soluble in water. At the same time, they have to be primary amines or secondary amines. And when it comes for tertiary amines, their hydrogen bonding ability is much, much decreased. For the same reason, because the number of sites available for hydrogen bondings are going to be lower. Now, when it comes for primary amide, in primary amides, like there are multiple sites for hydrogen bondings. This nitrogen atom can make hydrogen bonding with one water molecule, and there are two hydrogen atoms to make hydrogen bonding with two other molecules. And when it comes for secondary amide, there's only one hydrogen atom attached to nitrogen to make hydrogen bonds with water molecule. And in tertiary amide, there are no hydrogen atoms, but still nitrogen atom can make hydrogen bonding. So it doesn't completely diminish, but it's much limited. In this way, you can understand the water solubility of amides based on their hydrogen bonding abilities.